Okay, good evening. Welcome to
MathPractice number 206.
Except it's not evening, it's morning, right?
Yep.
Feels like evening.
Yep.
Alright, so we've been talking about infinity all week, and we're finally at the end. We've reached the end of infinity. You excited?
Yeah.
Alright. So today we're going to learn about one of the coolest things ever. This is one of the most amazing intellectual developments by any human being ever. And this is Cantor again. Mm-hmm. Alright?
Yep.
So let's talk about what we've learned so far. You take the integers, 0, 1, 2, 3, 4, 5, blah, 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 all the way up forever, and that goes to?
It goes to infinity.
Okay, now what if we only take the even integers?
They have the same number.
Yeah, you can match them up 1 to 1. And then, which was pretty surprising, right? It seems like there's more integers than even integers,
yeah.
But you can match them up. And then we learned all the fractions.
Yeah, and then the Hilbert Hotel.
Yeah, all the fractions even. And see, when you write in all the fractions on the number line, what does it look like?
It looks like a great purple line.
It looks like the great purple line. Yeah, it looks like you got all the numbers, right? It basically looks like a solid line all the way across. Looks like you got everything.
Yeah.
And there's the same number of those numbers as integers. Pretty incredible.
Yeah.
But you didn't get all the numbers, did you? Like, give me an example of a number that's not a fraction.
Maybe like 25.
Oh, 25 is the same as 25 over 1. So that is a fraction. A rational number. An integer over an integer.
Maybe E?
E! Very good example. E, which is about 2.71828 ... That's not a fraction. It's not a rational number. So we missed E. Can you think of another number we missed?
Maybe square root of 2.
Square root of 2 we missed. Very good. It's about 1.414. We missed that one. We missed pi, which is 3.14. Okay, so we missed a few numbers, but maybe we only missed a few. Maybe we can fit them into the Hilbert Hotel, right?
Yeah.
We can shift everyone over and get these three. But this is what Cantor discovered. Say we take just all of the numbers from 0 to 1, just the numbers here. Okay? We've got a lot of fractions in there, right?
Yeah.
But all of those numbers, a bus with all those numbers shows up. And we try to put them into the empty Hilbert Hotel, so nobody's there. We just put them in. So in room number 1 goes the number 0.1, 2, 3, 4, 5, 7, 8, 10, 1.
You forgot 6.
Oh, well, that's okay. ... In room number 2 goes 0.934862157 ... In room number 3, you make up a number that goes in room number 3. 0.2856.
0.285635897.
Okay. In room number 4 goes 0.6213046997 ... Okay?
Yeah.
And this goes all the way down forever. And these are just the numbers between 0 and 1. They're all 0 point something. Okay?
Yep.
Now the question is, if we go down to infinity, should we get all the numbers? And Cantor said discovered this amazing thing. Here, blue. If we take a new number, 0 point, and for the first digit, we look at the first digit of our first number. For the second digit, we look at the second digit of our second number. For the third digit, we look at the third digit of our third number. For the fourth digit, we look at the fourth digit of our fourth number, okay?
Yeah.
And the rule is going to be, we're going to make up a rule. If the digit we're looking at is a 3, change it to a 1. And if it's not a 3, change it to a 3. Okay? So if it's a 3, change it to a 1. And if it's not a 3,
change it to a 3.
Change it to 3. So our first digit we look at is 1.
Yeah, change that to a 3.
Change that to a 3.
And
this is
change that to a 1.
1.
3, 1, 3, 1.
So we're going to go out and we're going to make this new number. Okay? Whatever it is. Ours starts out 3131. But it's a new number, and it's different than every single one of the numbers we already have. Right? Because it's different by the first number in the first digit. This one's a 1, that's a 3. So those are different numbers, right?
Yeah.
It's different from the second number in the second digit. It's different from the third number in the third digit. It's different from the fourth number in the fourth digit. It's different from the 100th number at the 100th digit. Yeah, so we made a new number. So even if we think we made a list of all the numbers between 0 and 1,
There's always a new number.
there's always a number we left out, no matter what. Okay?
Cool.
So that means that there's more numbers in between 0 and 1 than can fit in the Hilbert Hotel. So there's more numbers than the integers, and there's more numbers than the rational numbers. So remember when we said we forgot a few numbers?
Yeah.
We forgot a lot of numbers.
Yeah.
So that these are called the real numbers when you fill in all the numbers.
Yeah.
So there's more real numbers than rational numbers.
Cool.
So the integers and rationals have an infinity that Cantor called Aleph null. This is the smallest infinity. Okay?
Yep.
The real numbers are bigger infinity. The bigger infinity. Whoa.
Cool.
Whoa. Whoa. So there's different kinds of infinities.
Whoa.
Can you believe that? Now, Cantor figured out a way to make different infinities. Aleph null, Aleph 1, he figured out how to make Aleph 2. I'm not going to tell you about that, but Cantor actually did figure out that there's Aleph null, Aleph 1, Aleph 2, etc. Okay?
Yep.
Different kinds of infinities. And there's a really neat problem saying which infinity are the real numbers. It's called the continuum hypothesis, but I don't want to go into that right now. So no one knows for sure if the real numbers are the next infinity or not. People think they are, but no one knows. Cool, right?
Yeah.
There's different kinds of infinities.
Cool.
You like thinking about that?
Yeah.
What's your favorite infinity?
Probably F null.
Aleph null.
Aleph null 8.
Aleph 8 is your favorite infinity?
Yeah.
Yeah, okay. Well, that's a pretty fun infinity. Maybe we'll go there someday.
Yeah.
All right. Good job, Steve. Good job.